Now let's look at the features supported by S9700. VLAN mapping can implement translation between carrier VLAN IDs and user VLAN IDs. The two PCs in this figure are in different VLANs on the same network segment. VLAN mapping between VLAN 2 and VLAN 3 is configured on GE1/0/1. When GE1/0/1 sends frames from VLAN 2 to VLAN 3, it replaces the VLAN tag for VLAN 2 with a VLAN tag for VLAN 3. When GE1/0/1 receives frames from VLAN 3, it replaces the VLAN tag for VLAN 3 with a VLAN tag for VLAN 2. This procedure allows VLAN 2 and VLAN 3 to communicate. VLAN mapping is not applicable if the PCs are on different network segments. Routers are used to implement communication between these PCs. QoQ mapping helps resolve problems that prevent devices on different network segments from communicating. This can occur if VLAN ID of the two nodes on different network segments conflicts or VLAN IDs on both ends of the public network are different. As shown in this figure, 2-to-1 QoQ mapping is configured on GE1/0/1.1 of switch 2 and switch 3. 1. GE1/0/1.1 of switch 2 receives a frame with an inner tag VLAN 10 and an out tag VLAN 20. 2-to-1 QoQ mapping is configured on GE1/0/1.1 to map inner and out tags of the frames received to tag 50 of the ISP network. 2. The frame sent by switch 2 is transparently transmitted on the ISP network. 3. After receiving the frame with ISP network tag sent by switch 2, GE1/0/1.1 of switch 3 replaces the inner tag VLAN 50 and out tag VLAN 60 with out tag VLAN 40 and inner tag VLAN 30. QoQ mapping maps VLAN tags on sub-interfaces, while QoQ stacking adds out tags on sub-interfaces as services require. QoQ stacking is useful, for example, because VLAN if interfaces do not support VLL. You have to access a VPN through a main interface. In such cases, multiple users cannot access the same physical interface. Use of the VLAN-based QoQ stacking function on different sub-interfaces allows multiple users to access the same physical interface. To access an ISP network in VPLS mode, you can use routing-based sub-interfaces, that is, enable QoQ stacking on sub-interfaces. SEP is a ring network protocol for use on the Ethernet link layer. SEP segments are the basic units of the SEP protocol. An SEP segment consists of a group of Layer 2 switching devices that are configured with the same SEP segment ID and the same control VLAN ID. An SEP segment uses a loop protection mechanism to block specific interfaces to eliminate network loops. When a link on the ring network fails, the device running SEP immediately unblocks blocked interfaces and performs link switchover to restore communication between nodes on the ring network. SEP has the following advantages. SEP can be used on complex networks. SEP enables Ethernet network devices to selectively block interfaces so that traffic is load balanced. SEP does not perform link switchover after link recovery, and this helps to make the network more stable. As shown in this figure, CE1 accesses the NPE through switches. A VRRP backup group is deployed on the NPE. Initially, NPE1 is in the master state and NPE2 is in the backup state. If a node or the link between NPE1 and LSW5 fails, NEP1 changes from master to backup state and NPE2 changes from backup to master. SEP is not configured. CE1 continues to forward traffic along the original path to NPE1, but NPE1 has become the VRRP backup device and does not forward traffic. Traffic forwarding is interrupted. SEP is configured. If FEP is enabled on the network, the blocked interface on LSW5 transitions to the forwarding state and sends link status advertisements to notify all the nodes to update their link state databases. Traffic sent from CE1 is then switched to the standby link. LSW5 to LSW2 to LSW4 to MPE2. This ensures uninterrupted traffic forwarding. MAC address flapping occurs on a Layer 2 network when the destination interfaces for MAC forwarding are constantly changing during the MAC addresses learning process. MAC address flapping is caused by a network loop or by an unauthorized user faking the MAC address of an authorized user to connect to the network. The existence of a loop causes a broadcast storm. All the switches affected by the broadcast storm suffer MAC addresses flapping. Layer 2 forwarding is incorrect. MAC address flapping detection can check whether MAC address flapping has occurred on the network. MAC address flapping detection is implemented as follows. The figure shows a connection that should not exist between switch C and switch D. When these two switches are connected, a loop exists between switch B, switch C, and switch D. When port 1 of switch A receives a broadcast packet, switch A forwards the packet to switch B. The packet is then sent back to port 2 of switch A. Switch A detects that the MAC address of the packet has flapped. If the MAC address changes between two ports frequently, switch A considers this MAC address flapping. Because switch B, switch C, and switch D form a loop, broadcast packets sent from other switches cause frequent, rapid MAC address flapping on the three switches. The number of MAC address flapping events on switch A is smaller than those on switch B, C, and D. This indicates that switch B, switch C, and switch D form a loop. MAC address flapping detection analyzes learned MAC addresses and allows a switch to detect traffic changes based on this analysis. The switch cannot, however, detect overall changes to network topology. Use of this function is limited to specific scenarios. To avoid MAC address flapping, MAC address anti-flapping can be configured on S9700 switches. The configuration can set a high MAC address learning priority on the interface. MAC address anti-flapping can be used to prevent unauthorized users from using the server MAC address to attack the network. You can run the MAC learning priority command to configure the MAC learning priority of an interface. If the same MAC address is learned by the interfaces with different priorities, the MAC address entry learned by the interface with the highest priority overrides the MAC address entries learned by the other interfaces. This prevents S9700 switches from learning MAC addresses of unauthorized users. Run the undo MAC learning priority command to prevent MAC address flapping between interfaces with the same priority. Loop detection and loopback detection. A loop on a network may cause a broadcast storm. Broadcast storms waste network resources and can cause services interruption on the entire network. Loop detection can detect loops. A switch with a loop detection configured sends detection packets to detect loops. If detection packets sent from one interface on a device are returned back to another interface on that device, a loop exists. This figure illustrates a network loop. Detection packets sent from GE1/0/1 on a switch are received by GE1/0/2 on the same switch. You are not advised to use a loop detection with STP. Unlike the loop detection function, the loopback detection function detects loops on the network that is attached to the device. A switch configured with loopback detection periodically sends detection packets to detect loops. If detection packets sent from an interface on the device are returned to the same interface, a loop exists on the network that is connected to the switch. As shown in the figure, if detection packets sent from GE1/0/1 of the switch are sent back to GE1/0/1, a loop exists on the network connected to the switch. Loopback detection only detects loops on a single node. It cannot detect or prevent loops on the entire network. Policy-based routing PBR forwards packets based on policies. PBR needs to be manually configured to ensure that packets are forwarded based on the policy. A PBR route is a static route. When the next hop is unavailable, the switch forwards packets based on the forwarding path that existed before PBR was configured. QoS policies are used to implement PBR. A traffic classifier that matches packets to a set of rules is configured. A traffic behavior is then configured to specify QoS actions. Finally, a traffic policy is configured. The traffic classifier is bound to the traffic behavior in a QoS policy. A switch connects an enterprise to a carrier network. The switch is connected to the internet through two links: a 1G link with the gateway 20.20.20.1/24 and a 10G link with the gateway 20.20.30.1/24. The enterprise requires that high-priority packets be guaranteed bandwidth. The 10G link is configured to transmit only high IP priority packets, such as those with priorities 4, 5, 6, and 7. The 1G link transmits low IP priority packets. This configuration guarantees high bandwidth for high priority packets. ARP is an open protocol that runs on Ethernet networks. It is simple and lacks security protections. When hosts and devices suffer an ARP attack, users may not be able to access the network, and CPU resources may be wasted. Even worse, users' information may be falsified or stolen. ARP attacks are classified as ARP spoofing or ARP flood attacks. ARP spoofing. The attacker sends an ARP packet to user A and deceives user A into believing that the gateway MAC address is 333. The attacker deceives the gateway into believing that the gateway MAC address is 333. The gateway then sends data that should be sent to user A to the attacker. If the routing function is enabled on the attacker could monitor and intercept packets that are forwarded between user A and the gateway. To prevent ARP spoofing, ARP security uses strict ARP learning, ARP anti-spoofing, dynamic ARP detection, and ARP gateway anti-collision. These defense functions protect communication networks against attacks by forged ARP packets. An ARP flood occurs when an attacker sends a large number of ARP packets in a short period of time. During an ARP flood, CPU firewall resources is wasted and the ARP buffer of the firewall overflows and fails to cache valid ARP entries. If the number of attacked packets continues to increase, responses may not get sent to valid ARP request packets, and hosts cannot access the network as a result. To prevent ARP flood, ARP security provides functions such as ARP packet suppression, ARP missuppression, and gratuitous ARP packet discarding. These defense functions suppress ARP packets to reduce the burden on the CPU and protect network devices against ARP attacks. S9700 core routing switches provide functions to defend against local attacks. The defense function for local attack limits the rate of packets sent to the CPU and discards packets that do not match rules. This ensures that services are processed normally. Defending the CPU against attack is the core of local defense. CPU defense protects the CPU by limiting the rate of packets sent to the CPU. S9700 switches can use CAR to restrict the number of packets sent to the CPU. CAR sets rates at which different types of packets can be sent to the CPU. CPU attack defense limits rate of packets in the following ways: rate limit based on protocols, rate limit based on queues, and rate limit for all the packets. If all the preceding rate limits are set, the smallest rate limit takes effect. The rate limit for packets of each protocol type is implemented independently. After a rate limit for a type of protocol packet is set, S9700 assigns packets of this protocol to a queue. Queue schedules are based on the weights of priorities. Services with the highest priority are processed first. If a rate limit is set for all the packets, the total number of packets sent to the CPUs is limited. S9700 switches can also use ACLs to configure blacklists and user-defined flows to filter attack packets. This figure shows LAN users connected to the internet through a switch and a router. The switch is connected to multiple users and receives many packets sent to the CPU. It is possible some of these are attack packets. If administrators find that Net1 users often launch attacks, they can add these attackers to a blacklist to prevent them from accessing the network. If administrators discover that falsified ARP request packets are attacking the CPU, they can set a rate limit for ARP request packets sent to the CPU. Smart link and monitor link. Dual uplink networking is widely used, but loops often occur on these networks. The smart link function can solve this problem. A smart link group has two interfaces, a master interface and a slave interface. The smart link function provides reliable link backup and fast link switchover. Smart link also supports a multiple instance function. Monitor link was also introduced as an extension to the smart link function. If the uplink interface status changes from up to down, monitor link detects the change and triggers the status change of the downlink interface. Monitor link then triggers the topology protocols of downstream devices to perform link switchover. In the figure, switch D connects to switch A. Smart link is configured on switch D. GE/0/1 forward state and GE1/0/2 is blocked and in backup state. This prevents switch D, switch C, switch A, switch B from forming a loop. If the link between switch B and switch D fails, Smart link can detect the fault and quickly switch traffic to the standby link. Smart link sends flash packets in multiple cast mode to notify other devices to update their MAC address and ARP tables. Smart link usually detects faults on the link that is directly connected to the interface on which Smart link is configured. Therefore, if the link between switch A and switch B fails, the Smart link on switch D cannot perform link switchover quickly. To enable the Smart link to respond to the link faults between switch A and switch B quickly, you can configure the monitor link function on switch B. When monitor link detects a fault on GE1/0/4, it forces GE1/0/3 to shut down. Active or standby link switchover is then triggered in the Smart link group on switch D. Association between BFD and VRRP. Association between VRRP and BFD helps implement active or standby VRIP switching within several milliseconds to ensure uninterrupted services. VRRP uses either of the ways described below to track the status of a BFD session to perform fast switchover. VRRP uses BFD to monitor upstream links. This enables the master device to faster detect network faults. When a fault occurs, the master device lowers its priority to trigger a switchover. The backup device replaces the master device to ensure that uplink works normally. Switch A in the figure functions as the master device for traffic forwarding. Switch B is the backup device in the standby state. Switch A uses BFD to detect the status of the link between switch A and switch C. If a fault occurs on this link, switch A detects the link fault within milliseconds and sends VRRP packets with a low priority to switch B. If the priority of switch B is higher than priority in the VRRP packets, switch B becomes master device and functions as the gateway to forward data on the network. This ensures uninterrupted communications. The backup device can also use BFD to monitor the status of the master device. If a fault occurs on the master device, the backup device preempts the master device. Switch A in the figure functions as the master device for traffic forwarding. Switch B is the backup device in standby state. Switch B uses BFD to detect whether the IP address of switch A is reachable. If a fault occurs on switch A, switch B immediately detects the fault and becomes the master device to forward data to network hosts. Two types of detection can be simultaneously configured to ensure fast switchover when a network fault occurs. Finally, let's learn the way to delete configurations on the interfaces by one key operation and the way to display interface configuration. Deleting interface. Configurations one by one is very time-consuming. You can run the clear configuration interface command to delete all the configurations on an interface. After configurations are complete, you can run the display this command to check the current configurations.